So now let's do a simple term structure model in continuous time. I'm going to do the exact same model with the exact same ideas. It's just a slightly different notation, and by having seen the ideas in discrete time, I hope that'll make the method that we use go down much easier in continuous time. So let's write down the same model as we just did, the Vasicek model in continuous time. I'll start with a short rate process, so an AR1 for the short rate of interest. This is what I called X previously. We might as well jump ahead and recognize that it's going to come out as being the interest rate. So there's an AR1 for the interest rate. And as a matter of notation, that's the special case of the AR1. Let's call mu sub r as the more general case of a short rate process that depends on its own level. We'll have a discount factor as usual. We'll find the term structure of interest rates by the expected future discount factors. What's the answer going to be when we're all done? Always nice to know where you're heading. The forward rates are going to look just as they did in discrete time. There's an expectations term, which in continuous time is geometric decay from the current interest rate. Then there's a risk premium term. It has the market price of risk sigma lambda in there, and it takes care and the half sigma squared terms that we had before. Okay, how do we get from there to there? Same method. First, let's guess that the bond price is going to be a function of maturity and the state variable, today's interest rate. There's no reason any other variable should matter because today's interest rate tells us everything we need to know about where things are going in the future. So we'll find a partial differential equation for P of NR from the instantaneous pricing ideas, just as we found a difference equation in discrete time from the idea of instantaneous pricing. Well, what does pricing mean in continuous time? Here is our generic continuous time pricing relationship. Expected return minus risk-free rate is covariance of discount factor with return. So let's apply that to the price that we're using to the bond price. The expected return is change in price minus dPdN, and there's the risk-free rate, and there's the covariance term. That all looks familiar, except what's that dPdN thing doing here? Well, the way we do things in term structure is we've defined the price here as a function of maturity, not as a function of the due date of a particular bond. So as I look one period forward, P of n refers to a different bond. So this just captures the fact that when we move one step forward, we have to look at the price of a bond that is a little bit younger. Okay, so that's the basic pricing relationship. Next thing we do is we apply Ito's lemma to our pricing function. So if P is a function of n and r, then of course Ito's lemma just says that dP is its two derivatives with respect to r. N doesn't change over time, and there is the dz term. So now what we do is we substitute B into A. We substitute the dP term into the instantaneous pricing term. And what do we get from all that? Well, we want to put B into A. So there is dP dr mu r. That's our first term. This is the E of dP over P term. Next term, dP dN term. That's just dP dN, the Rp. And then this term here is dP dr sigma r times the discount factor sigma lambda. Rearranging things, I like to put dP dN on the left and all the other terms on the right. And now stop and take a deep breath and look at what a beautiful thing we have. This is the general bond partial differential equation. It tells you as a function of r derivatives on the right-hand side what is the n derivative on the left-hand side. This works just like the Black-Scholes differential equation that we derive for bond pricing. And the ideas are all very clearly related here. You start with the price of a maturing bond is 1, and then this equation tells you how you can get to bonds of a slightly different maturity. This tells you how to work up the maturity schedule from maturity 0. So it's a partial differential equation, and one can solve that thing numerically just as we talked about solving the Black-Scholes differential equation numerically. From the spatial derivatives, you go to the maturity derivative, and that lets you work forward through the maturities. We'll be even more clever. Now let us guess that this p of nr function is a log linear function. And just as we did in discrete time, we'll find the a,n, and b,n, this time from a differential equation rather than from a difference equation. So how do we do that? Well, given this guess, then the derivatives of p that we need, the dp dn and the dp dr, those are easy to find. Those are the derivatives of p from that function. Next, we take these derivatives of the guessed pricing function and we plug them into the bond differential equation. So what do we get? This is dp dn on the left-hand side, and there's the mu r term on the right-hand side. There's the 1/2 sigma squared term. There's the rp term. Once again, just as in discrete time, my result here now, I have a constant term and a term multiplying r. Those separately have to be equal to each other. The constant terms have to be equal, and the terms multiplying r have to be equal. So the terms multiplying r, there's a bn there. What else multiplies an r? There's a phi multiplying an r, and there's a 1 multiplying an r. And that phi multiplying an r also had a bn attached to it. So b prime of n is 1 plus phi times b of n. Same thing for the a terms, the a prime of n on the left, and then there's all this junk over on the right. Now, let's look at what we have. We have now a differential equation, an ordinary differential equation in n to solve in order to figure out our bond pricing. This makes life a lot easier. This is the trick behind this class of models. We started with something hard, either solving a stochastic differential equation and taking an expectation. That's how I did the Black-Scholes formula. It worked there. Boy, it would be a mess to do that here. We could have solved lambda forward, then take the expectation to find the bond price. That would have been hard. It's not that hard for a computer. A computer can simulate the lambdas forward and take the average. But even that is time intensive for a computer and very time intensive for a person. Our first step was we turned that into a partial differential equation with nothing stochastic. Well, that makes it a little bit easier. Solving partial differential equations, at least there's no randomness, but it's still, it's okay numerically, still kind of hard for normal mortals. Now what we've done is we've turned that into an ordinary differential equation. That's really fast if you have to go numerical, much faster than partial differential equations. And in this case, it's something we can do by hand. So the b prime of n, for example, that one is an easy differential equation to solve. What does that mean? That means db dn is 1 plus phi b. We can just take the 1 plus phi b and left on the n on the right and integrate. If you integrate that out, then exponentiating b of n is 1 over phi 1 minus e to the minus phi n. So this formula for the b of n's in continuous time looks exactly like the same formula we got in discrete time, and the method is exactly the same. What have we done? From pricing, we've found how prices have to spread across maturities, and then by guessing a linear formula, that spreading across maturities turns into an ordinary differential equation for these coefficients spreading across maturities. Those ordinary differential equations are, in this case, easy to solve, more generally easy to solve numerically. That's how we get to the model we're looking for.